Hello and welcome. I'm Qian Wengao from the Institute of Software at the Chinese Academy of Sciences. I'd like to share a research paper entitled MPC in the Head Framework Without Repetition and its Applications to the Lattice-Based Cryptography. This research is a joint work with Wei Hao Bai, Long Chen, and Zhenfeng Zhang. Before delving into our research, let's first revisit the fundamental concepts of the zero-knowledge proof. Zero-knowledge proof enables the prover to convince a verifier that it has a secret witness without leaking any information about it. And it has wide applications in network authentication, cryptocurrency and blockchain system, and privacy-preserving technology like anonymous credential and so on. Well, now zero-knowledge proof aims to produce a valid proof about an NP relation R on a statement X with witness W. A zero-knowledge proof protocol must satisfy the following properties. The completeness means the proof produced by honest prover can be always pass the verification. And the soundness means that an adversary without access to the witness cannot produce a valid proof to convince the verifier. Well, finally, the zero-knowledge property implies that verifier cannot extract any information about the witness via proof. Finally, there exists a simulator even without access to the witness. It also can produce a transcript that is distinguishable from the real one. For certain zero-knowledge proof, we can utilize a distinct asymmetric circuit C to characterize the NP relation it proves. We take the statement X and the witness W as inputs to the circuit C such that the output of C is 1 if X and W satisfy the NP relation, and 0 otherwise. This circuit is specifically tailored to the statement X. Non-interaction zero-knowledge proof is a specific type of zero-knowledge proof. Prover can use it to produce a valid proof without any interaction with the verifier. This means that a non-interactive zero-knowledge proof can be verified by anyone publicly, which is a powerful tool in building practical cryptographic protocols. Now let's review the MPC in the head paradigm. The MPC in the head paradigm is introduced in IEEE at 2007. It is an innovative approach to construct the knowledge proofs. It inscribes the NP relation to be proved at the circuit C for MPC computation and require the prover to locally simulate the computation of underlying MPC protocols carried out by multiple participants. Well, the transcript of each participant is then committed and sent to the verifier. The verifier randomly selects a subset of all participants and asks the prover to open their transcripts. Finally, the prover opens these transcripts and sends them to the verifier for finally checking. By selecting a subset based on a random oracle, we can convert this interactive approach into a non-interactive mode. The correctness of the zero-knowledge proof is rely on the correctness of the underlying MPC protocols, while the property of zero-knowledge is derived from the underlying MP's privacy properties, which means that even if an adversary compromises up to T parties, it cannot obtain the secret of the remaining parties. We focus on the soundness. For soundness, if an adversary has no access to the witness, it has to tamper with the will of MPC participants, which happen under the probability of O T/N. Well, To get the negligible soundness error, the prover must repeat the MPC evaluation up to lambda times. As a consequence, the proof size and the proof time is proportional to lambda, exist the security parameters. Overall, MPC in the head framework just relies on the hash functions, which can be used to construct post-quantum security protocols, and it also can run efficiently when proving small circles. Where there are some disadvantages of MPC in the head. Just like compared with the thickest NUC, it has a constant proof size. The proof size of MPC in the head-based ZKP is linear to the secret size. So a natural question is that, can we further improve the efficiency of the MPC in the head approach? Well, in this paper, we design a novel and more efficient universal interactive technology proof protocol based on ethical multi-party computation. We named it DITE. The DITE removed the reputation in previous MPC in the head approach and reduced the computation cost and the computation size from lambda to 01. We also show that this result can be used in building efficient knowledge of secret key proof for lattice-based post-quantum key encapsulation mechanisms like Kyber and Frodo. Okay, let's review the CAM-TLS protocol. It is a post-quantum variant of transport layer security. It uses a post-quantum CAM instead of a signature to complete the authentication. CAM-TLS provides lower computation costs in server side and lower communication traffic between the client and the server. However, a tricky problem is how to manage the certificate that embedded the secret key of a post-quantum CAM. Well, in existing internet infrastructure, like PKI system, the certificate holder must apply for certificates from the CA to verify their identities. During this process, the holders are required to provide a proof of the knowledge for their secret key corresponding to the public key in the certificate. That is, the proving of the secret key protocol. For short, is KOSK. However, for the public key associated with post-quantum key encapsulation mechanisms, there currently aren't efficient proof of knowledge scheme available. This is due to the mismatched parameters where, for example, the dualism signature cannot be used as a proof of knowledge of the secret key for lattice-based CAMs like Kyber and also other schemes. So our solution addresses this challenge by offering a proof of knowledge of the secret key for CAMs such as Kyber in just 0.68 seconds. So let's give a short look of the technique we used. First, we chose the Shamir secret sharing to replace the original additive secret sharing. By doing this, we are able to check the broadcast shares in the underlying MPC protocol evaluation if they are in the same polynomial. If a malicious adversary intends to modify the result of the MPC protocol, it must do tamper n-d shares. Well, in this case, we can reduce the soundness error from 1/n for additive sharing to dt/nt for Shamir sharing. We carefully manage the binomial coefficient. We can make the soundness error to be negligible small. For example, we let the t be 100 and d equals to t at 1, and let n be the 2 times of t. The soundness error is approximate to negligible. Further, to reduce the proof size, we use the packed secret sharing, which can embed more than one secret in one polynomial. Thus, we can reduce the computation cost and the process from O lambda to O1. Also, we design new approach to check the correctness of the MPC evaluation result instead of complete the MPC exclusion. This causes that there is no need to produce B or triples in pre-processing phase. Alternatively, this method allows the prover to present addition random shares denoted as D-degree polynomial Z. For the multiplication gate, the prover demonstrates that x times y minus d equals to 0. And so Z is indeed the multiplication of x and y. Subsequent computations are then performed on the degree D polynomial Z. However, to enable the diet method to prove any circuit efficiently, it is crucial to develop a highly efficient technique for verifying linear transformation gates, especially in the context of packet sharing. Once it is established, this approach allows for vector-based computations to be universally applied across various circuit design. Such computations encompass a range of operations, including L-fold addition, L-fold multiplication, and permutation within L-dimensional vectors. Due to time constraints, the specific case of these techniques will not be explained here, and you can get it in our full paper. Concurrently, in order to achieve universal proof capability, we implement the addition, multiplication, and linear transformation gates for the diet. This table lists the asymptotical complexity improvement of diet. For multiplication gate, we reduce both size and computation cost from O lambda L to OL, and for the addition gate, the computation cost is also reduced to OL. And for linear transformation gate, the space and the computation complexity are both OL. Well, this is all. Thank you for your listening.